The era of silicon photonics mass production is officially here, facing the limits of AI computing power in the 2-nanometer era. TSMC made it clear, future data transmission must switch from electricity to light. Because when it comes to computing, electrons are unmatched. But when it comes to transmission, photons are superior. This has sent giants like Nvidia, Intel, and Broadcom racing into the CPO track. However, as optoelectronic components shift from independent modules to highly integrated chip packages, the complexity of reliability validation has skyrocketed. The biggest headache for engineers right now is, where on earth are the standards? Since there are no dedicated standards established for CPO just yet, everyone is still relying on the industry's most authoritative guideline, a standard that's been around for over 20 years, Telcordia GR-468. But facing the rapidly evolving silicon photonics technology, can this old standard still be trusted? Hello everyone, welcome back to iST Ease Your Pain. I'm your host, Katelyn. If you want to grab the latest first-hand insights on semiconductor technology and validation, don't forget to subscribe and turn on the notification bells. Many people ask, since GR-468 is a product of 2004, why is it still the mainstream today? The truth is, its cross-domain coverage is incredibly robust. It not only covers the entire optoelectronic chain, including laser diodes, LD, photodiodes, PD, and modulators, but it also breaks down assembly maturity into 5 validation tiers, from bare dies to submodules and complete optical modules. More importantly, GR-468 strictly differentiates between central office, controlled environments and uncontrolled environments, outdoors. This is crucial for system developers because the application scenario directly dictates the stress conditions. Imagine if your equipment has to operate outdoors or under extreme temperature swings. If the optical alignment shifts even a tiny fraction, the signal is completely ruined. GR-468's rigorous demands for environmental stress are exactly what ensure your product can hold the line under these extreme scenarios. Furthermore, it emphasizes both qualitative and quantitative metrics, allowing you to not only qualify mass production but also accurately estimate system lifetime. If the GR-468 standard is so rigorous, why do systems still crash in practical applications? Many products manage to pass environmental stress tests, yet they still experience mysterious signal degradation during system bring-up or long-term operation. This is because under the CPO architecture, the interactions between optical, electrical, thermal, and mechanical forces are far too complex. Pass-fail logic just doesn't cut it anymore. The first major hurdle is the thermodynamic contradiction. The GPUs handling core computing can easily heat up to 100 degrees Celsius. However, the laser light sources in silicon photonics, which are extremely temperature sensitive, will experience thermal drift or even a shortened lifespan if they exceed 70 degrees Celsius. To resolve this contradiction, the industry has turned to external laser sources, basically plugging in the laser light source like an external battery. But adding another connection interface introduces new risks. Things like fiber bends, microdust, or mechanical microcracks can cause insertion loss to spike, creating potential failure points in the system. To address this, iST recommends performing HTOL by continuously powering the device at 85 degrees Celsius or higher for thousands of hours. We can observe the optical power degradation curve of the laser source to project whether the product can sustain a system lifetime of over 10 years. The second hurdle is the stress tug-of-war in heterogeneous integration. Silicon, glass, and metals all have completely different coefficients of thermal expansion. When they heat up during operation, they pull against each other, leading to chip warping or structural delamination at worst. iST suggests utilizing TC by drastically cycling temperatures between -40 degrees Celsius and +85 degrees Celsius. We verify whether the optical module alignment shifts, rather than just checking if the components can still power on. Additionally, high temperature and high humidity environments can cause the UV epoxy used for fixing to age, swell, or creep, directly resulting in signal loss. iST recommends running THB by applying voltage in an environment of 85 degrees Celsius and 85% relative humidity for over 1,000 hours. We can ensure the structural toughness of the adhesive materials under extreme conditions. As AI computing environments become increasingly harsh, future standards will lean heavily toward requirements like anti-sulfur and salt spray resistance. Don't let reliability validation just be a piece of certificate. It should be the very bedrock that supports long-term system stability. If you run into any challenges during your silicon photonics R&D or bring-up process, please feel free to contact iST at any time. To learn more about silicon photonics and CPO validation technologies, join us on LinkedIn or Facebook. If there's a topic you want to see, drop it in the comments. That's a wrap for today. See you. Like, subscribe, share, turn on the notification bell so you won't miss out.